A good day to all of you. In today's session, we will look at another one of these basic power converters belonging to the family of non-isolated converters. We had seen in the last session that such a cell, a converter cell consisting of a single pole double throw switch and an inductor with two throws T1, T2 and a pole formed the basic power converter cell, and with this we were able to make several ways of converting power, DC power, from one voltage to another or from one current to another. And we had seen that the first type of power converter circuit that we saw consisted of connecting a voltage input, voltage source to this basic converter cell and a load resistance R supported by a capacitive filter at the output of this power converter cell, and we saw that this was classified with the name of buck power converter, where the output voltage V naught was D times the input voltage V g, and output voltage was always less than the input voltage. The D varies from 0 to 1, and because of this reason, this non-isolated converter was called buck converter. It was bucking the input voltage and providing an output voltage which was less than the input voltage. We had also seen that this basic cell could be used in three different variants to form different basic power converter cells. The first one and the second one we had already seen, called the buck power converter, the boost power converter, and what we will be seeing today will be the third converter, which goes by the name of buck boost or flyback power converter. In the first type of power converter, the input was a voltage and output was a current, and we could say that this is a voltage input, current output power converter. And the second converter had current as the input and voltage as the output, and we could say that as a current input and voltage output power converter, which boosts the output voltage. In this converter, V naught is V g divided by 1 minus D, where D is varying in the ratio of 0 to 1, and this converter was boosting the input voltage. The input current is stiff and output voltage is stiff, and we could call this as a current input and voltage output variant. The third variant that we are going to see today is the current input and current output variant, where the input current and the output current are both stiff on account of the inductor which is getting charged from the source and discharging into the load. And this converter is called the flyback power converter. And in this lecture today, we will see several of the features of the flyback power converter. So, we will limit our analysis during today's lecture to the flyback variation, which is the third variation of the power converter. This converter is having the name flyback power converter or buck boost power converter, because this is capable of providing an output voltage which is both less than as well as more than the input voltage. So, we will see the analysis process during this 1 hour of lecture. Okay. And we had seen that the steady state analysis of all these converters consists of the voltage gain V naught by V g as a function of the duty ratio D. This is one of the first things that we would like to find out. And similarly, the current gain or the output current to input current ratio, again as a function of gain. These are the desirable characteristics of the power converter, but the converter has a number of undesirable characteristics. For example, the inductor currents are not perfectly constant, and there is a ripple in the inductor currents, and these ripples can be quantified by the ratio of delta I by I. How much is the variation in current in relation to the steady current that is flowing, and similarly delta V by V on the capacitor tells us how much is the variation in the voltage as a fraction of the DC voltage. So, all these quantities are undesirable quantities. These are the current ripple and the voltage ripple. And then the analysis also takes into account the non-idealities of several of the components that are present here. The non-idealities of the switch, the non-ideality of the source, and the non-ideality of the storage elements, which are the inductors and the capacitors. And eventually, we also like to find out what is the efficiency of power conversion, which is the ratio of the output power divided by the input power. This is what we would like to find out through the process of our analysis. And this analysis is done based on several simplifications on the operating performance. So, the first question is, what is the ratio of output voltage V naught to the input voltage V g, voltage conversion ratio, and the converter is operating at a constant switching frequency during the on time of the switching frequency. If you call a switching frequency as consisting of a total duration of Ts, out of that there is a duration called T on and there is a duration called T off, and during T on the switch is connected to P T1 and during T off the switch is connected to P T2. So, under that condition, if everything is ideal, inductor does not have any resistance, the switches do not have conduction drop, the switches operate instantly. With all these simplifying assumptions, we like to know what is the ratio of V naught by V g, and this is obtained by applying the inductor volt second balance. We have done this twice before, once for the buck converter and once for the boost converter. The method is very simple. Find out under steady state what is the voltage across the inductor, what is the periodic voltage across the inductor. So, in one period which is 0 to Ts, the voltage across the inductor is V g during the on time, because the switch is connected to P T1, and during the off time the switch is connected to P T2 and the voltage across the inductor is V naught. V naught is applied across the inductor, and we see that the inductor is applied a positive voltage during a portion of the switching period and a negative voltage during the next part of the switching period. And the principle that is used in order to find out the relationship between V naught and V g is that the inductor on an average does not support any DC voltage, or the periodic DC voltage of the inductor is 0, or as we see here, the positive volt second across the inductor is the same as the negative volt second across the inductor during the off period. So, if we apply this volt second balance on the inductor, we can write the equation that during the on time the inductor is applied a voltage of V g, because the switch is connected to P and T1, and during the off time the switch is connected to P T2, and at that time the voltage applied is V naught. So, the volt second on the inductor is during the on time V g T on and during the off time V naught T off, and if you equate it to 0, which is the voltage across the inductor on an average over one switching period, we find out the ratio of V naught by V g is minus T on by T off, which is the ratio of on time divided by off time, or D, duty ratio, divided by 1 minus D, the complement of the duty ratio. The important point is there is a minus sign here. This is minus D by 1 minus D. What it signifies is that for a positive voltage Vg, the output voltage will be in the negative direction, which is V naught is negative. That is what this minus sign signifies. So, we apply this volt second balance and we find out that the inductor has, or the output voltage is minus D times D divided by 1 minus D times input voltage. This can be plotted, this ratio, this function of D of this V naught by Vg can be plotted as a function of D, and you see that it starts from 0 when D is 0 and it goes to infinity when D is 1, and this would be the ideal gain characteristics of the flyback converter. So, as D varies from 0 to 1, the gain varies from 0 to infinity. When D is equal to 0.5, the gain will be 1. When D is 0.5, the gain is 0.5 divided by 0.5, which is 1. Input and output voltages will be equal. The ratio of Ig by I naught is found simply by current conversion, or this is defined as current conversion ratio, and this can be found out by averaging the output current. We see that this I naught T is the same as the inductor current during the off time, and inductor current is IL, it does not have any ripple. So, this current during the off time is flowing through the load, and so the average of that is IL into T off, which is equal to I naught into Ts, and we can say that IL is I naught into Ts by T off. This is the average input current. In the similar way, average input current can be seen as during T on, IL is same as Ig, rest of the time Ig is 0. So, it is possible to find the relationship between the average input current and the inductor current. So, this also has the relationship as shown here. So, if we combine these two quantities, which is the inductor current, we find that the input current average divided by T on is the same as output current average divided by T off, or the ratio of the input current to output current is minus D by 1 minus D. We had also seen in the other converters that this ratio V naught by Vg in the ideal case will be the same as Ig by I naught. So, that the efficiency of the power converter, which is V naught I naught by Vg Ig equal to 1. So, on account of conservation of energy and because there are no losses in the ideal converter, V naught by Vg will be the same as Ig by I naught, and which is this ratio D by 1 minus D. This result, similar results we have seen for the buck converter and the boost converter, and we are seeing the same thing following similar lines of analysis. And the efficiency is given by the ratio of voltage conversion and current conversion, which is 1, and this is what we expect in the ideal case. The non-idealities are the inductor current ripple and the capacitor voltage ripple, and this is found out. The current ripple or delta I in the inductor is found out by integrating the voltage across the integral of inductor voltage will give us what is the current ripple. The inductor is applied voltage of Vg during on time and V naught during off time, and if we integrate this voltage, you will see that during the on time this positive voltage Vg results in an increase in the inductor current. During the off time, the negative voltage that is applied across the inductor results in a drop in current. Under steady state, the rise in current during on time is the same as drop in current during off time, and we can write this delta IL or the ripple current as the slope Vg by L and multiplied by on time, which is D times Ts. So, the inductor current ripple is related to the input voltage and inductor through the on time. It is always good to represent the voltage ripple as a fraction of the current through the inductor, the current ripple as a fraction of the current through the ripple, and when we do that, this IL is related through the output current V naught by R divided by 1 minus D, delta IL we had just now found out V naught by L into 1 minus d Ts, and if we combine these two quantities, we get the ratio of the ripple current to the average current in the inductor, which is 1 minus d whole square Ts by L by R. Ts is the switching period and L by R is the time constant of the load and the inductor. And if this ratio, switching time, is very much small compared to the time constant of the converter, then this ripple will be small, and that could be one of our condition for design of the converters. So, we can say that for low ripple current, as the performance of the inverter for the inductor current to reach the ideal condition, it is necessary that this inequality is met better. Ts, if it is becoming a smaller and smaller fraction of L by R, then our inductor ripple current will go towards 0. So, the design criterion is that the switching period Ts must be very small compared to the circuit time constant L by R. The non-ideality in the converter on account of the switches having non-zero drops can be found out by finding out what is the voltage drop in the switch when it is on and what is the voltage drop in the diode when the diode is conducting. If we apply these non-idealities, we will come across a different ratio of V naught by Vg, but we apply again the same principle, which is the volt second balance. We keep account of the voltage drop. The volt second balance on the inductor is now Vg, supply voltage, minus the device drop, the transistor drop during on time, and similarly the output voltage plus the diode drop during the off time. And if we now take the volt second balance, we find that you will say, if we see this V naught plus Vd, that is because the polarity of V naught is negative. On account of that, this ratio, the on time voltage is algebraically Vg minus Vt into T on, off time voltage is algebraically V naught plus Vd into T off, and from this volt second balance we get the ratio of the output voltage to input voltage is the same as the ideal gain d by 1 minus d multiplied by a correction factor. You can see that this correction factor consists of two parts, a numerator which is 1 minus Vt by Vg and a denominator which is 1 plus Vd by V naught. If the correction factor has to approach 1, then the device drop Vt has to be small compared to the source voltage Vg, and similarly if the denominator has to approach 1, the diode drop Vd has to be small compared to the output voltage V naught. And from this we can also say that the efficiency is the factor by which the voltage ratio is different from the ideal voltage ratio, which is 1 minus Vt by Vg by 1 plus Vd by V naught. If you look at the circuit, this term also can be, this efficiency can also be seen as two terms, one consisting of a numerator and another consisting of denominator. The numerator is effectively 1 minus Vt by Vg. You can say that it is the efficiency of charging. From Vg, we lose the voltage drop and rest of it goes into the inductor. So, you can say that the numerator represents the efficiency of charging, and the denominator 1 plus Vd by V naught represents the efficiency of discharging, because during discharging of the inductor, the current passing through the diode drop is loss and current passing through V naught is the output load, output power. And so, this nicely can be decomposed into two parts, numerator as the efficiency of charging and the denominator as the efficiency of discharging, and it nicely fits in, and this number will always be less than 1. And if it has to approach 1, Vt has to be very much less than Vg and Vd has to be very much less than V naught. Okay. We had also seen that none of these series non-idealities, Vt of the switch or Vd of the diode, they are all series non-idealities. It does not affect the current conversion ratio, and they remain, the current conversion ratio Ig by I naught remains the same as the ideal number, which is minus d by 1 minus d. And when we multiply these two terms, we get our efficiency, which is 1 minus V t by V g divided by 1 plus V d by V naught. The method of evaluating the voltage gain, current gain, the current ripple in the inductor, the efficiency on account of the switch drops, they follow the same method. Volt second balance on the inductor, integrating the inductor voltage to get the inductor current, and so on. The inductor has another non-ideality, which is a resistor. So, no inductor can be with 0 resistance, as we are using a conducting wire to wind the inductor. It has a resistance which is R L. On account of that, the output voltage V naught by V g will be different from what we calculated in the ideal case, and that also can be found out from again the volt second balance on the inductor. During the on time, the inductor is applied a voltage of V g minus I L R L, and during the off time, the voltage across the inductor is output voltage plus I L R L, and if you find out the ratio of these areas and equate it to 0, V g minus I L R L t on first term and V naught minus I L R L t of second term, if both of them are made equal to 0, then on simplification we find that we have an expression which relates V g and V naught through the non-ideality of the resistor R L by R and the duty ratio D, and on simplification, if we apply this term alpha equal to R L by R, the parasitic resistance of the inductor can be normalized by the load resistance R, and that ratio is defined as alpha. So, if we define like that, then V naught by V g can be written as the ideal ratio V naught by V g multiplied by a correction factor 1 by 1 plus alpha by 1 minus d whole square. This alpha is the ratio of R L by R. So, we have seen that now by an amount which is 1 by 1 plus alpha by 1 minus d whole square, the voltage gain is reduced from the ideal, and this number will always be less than 1 because it is 1 by 1 plus some positive quantity. And this correction factor being less than 1, we can also say that this correction factor is the same as efficiency. The efficiency of power conversion is the same as this correction factor 1 by 1 plus alpha by 1 minus d whole square. Interestingly, this correction factor is identical for the boost converter as well as the flyback converter. So, on account of this correction factor, V naught by V g now is not just d by 1 minus d, which is shown by the red color line here. It is getting modified by a correction factor, and once the correction factor is included, the gain of the converter drops to 0 as you go to duty ratio 1. It reaches a peak at some point, and then instead of going all the way to infinity, it changes direction and falls all the way back to 0. So, as duty ratio is 0, the gain of the converter is 0, and as the duty ratio goes to 1, also the gain of the converter is 0, and in between there is some value for which the gain is maximum, and it is possible to find out what is that value of duty ratio at which this gain is maximum, and also what is that maximum gain. All this can be found out by simply analyzing this factor, and this function has a maxima and minima, and if we differentiate it with respect to duty ratio and equate it to 0, we can find out that this maximum occurs at a duty ratio which is 1 minus root alpha, and the maximum value itself is 1 by 2 root alpha, where alpha is the ratio of the parasitic resistance to the load resistance. This alpha is the inductor resistance normalized to the load resistance, and this is the real forward gain. What you see as the blue line here, it is modified from the ideal on account of the correction factor that we see here. Now, we can also find out the efficiency of the power conversion and plot it on the same graph, so that we get certain other insights into the operating characteristics of the converter. The efficiency is also a function of alpha and d, and on this same figure for d, if we plot efficiency in the vertical axis, for duty ratio, exactly at the point where maximum output voltage is obtained, at that time the efficiency turns out to be 0.5, or at that operating point only half of the power is delivered to the load, the remaining half is lost in the converter. That is not a very satisfactory state of things, and so we would like to operate at the lower end of duty ratio where the efficiency is more than 0.5. What you see here in the yellow region here is the region where the gain is in the increasing range, where it has not reached the maximum. So, in that region gain is more than 0.5, and on the other region, in the next region, the efficiency is less than 0.5, and that is not our preferred region. Our preferred operating region is the region where efficiency is greater than 0.5. It is what is shown here. The next non-ideal performance of the converter is on the output voltage. Output voltage has V naught plus delta V naught, and this delta V naught can be found out by finding out what kind of current is coming out of this. Out of that, all the DC current will go to the load and the AC current will go into the capacitor, and by integrating this current in the capacitor, it is possible to find out the output voltage ripple. This is the same strategy which we have followed in the other converters as well. I have plotted the current I naught of t, which comes out of the converter. What is here is a function of t, and then the current, load current going into the load is a flat current I naught. So, the difference between I naught of t and I naught, what is shown in hatched region, is what is going into the capacitor current. So, the hatched region here is capacitor current. It has a negative value in the on period and a positive value in the off period. During the on time, the capacitor is discharging its energy into the load on period of the switch. During the off period of the switch, the capacitor is getting energy from the source and the load is also being supplied. So, by integrating this capacitor charge, we will be able to get what is the voltage ripple on the capacitor, and that integral gives you here delta V naught. Delta V naught can be found out by finding the hatched region on this side during the off period or the hatched region during the on period. On period current being constant, it is easier to do the integration. So, we find that I naught into dTs is the area here, and this area multiplied this I naught multiplied by dTs is the current taken from, charge taken from the capacitor divided by the value of C will give us delta V naught, and that is output voltage multiplied by on time divided by RC time constant of that. Again, it is good to represent it as a ratio, normalized it on the output voltage. So, this is duty ratio times switching period divided by the load time constant, and the design guideline to keep the unwanted ripple on the output becomes clear from this, that if the switching period Ts is very much less than the load time constant RC, then we will have low ripple, and that could be our design guideline, and this is obtained by the capacitor charge balance. So, practically now we have done the ideal as well as the non-ideal steady state analysis of this converter, and we see that the ideal voltage gain of this converter is V naught by Vg, which is minus d by 1 minus d. This was obtained by applying the volt second balance on the inductor. This was our method of evaluating the ideal voltage gain. The ideal current gain is obtained by averaging the current through the input as well as the output and relating it to the inductor current which is in between, and this also turned out to be a function of d, and we have seen that this ideal voltage gain and ideal current gain, ideal forward voltage gain V naught by Vg and ideal reverse current gain Ig by I naught, both will be same, so that the product of them will be 1 to keep the efficiency 1, or to keep that the losses are 0 in the converter. V naught by Vg will be the same as Ig by I naught. So, that the efficiency in the power converter is 1. This was the second ideal performance characteristic that we found. This was obtained by averaging the current. The ideal voltage gain was obtained by finding out volt second balance on the inductor and equating it to 0. The current ripple is an undesirable performance in the converter, and we try to normalize it as a ratio of ripple current divided by the inductor average current, and that also was found out by evaluating by integrating the inductor current and finding out the ripple current in the inductor and normalizing it to the average current in the inductor. This turned out to be the ratio of Ts by L by R with a multiplier 1 minus d whole square, and this gave us the design criterion for the current ripple to be very small, that Ts has to be very much less than L by R. So, many times R being the load current is not under our control, but the inductor in the power converter is what we have to provide, and that inductor value can be selected appropriate to the switching period, so that the current ripple is small or negligible. In the next step is the voltage ripple on the converter, the voltage ripple on the output voltage. Again, this also has been normalized, so that it is represented as a ratio of the switching period divided by the RC time constant, and this could be used profitably. The load resistance in the converter is not under our control, it is decided by the user, but the capacitor that is used in the converter can be selected, so that the voltage ripple will be small and negligible. So, these undesirable quantities of delta I and delta V has to be very much less than I and very much less than V. That criterion can be used in order to select L and C. The first one, if this is used, if you know what is V naught and Vg, this can tell us at what operating duty ratio one should operate, so that the converter does the power conversion with the voltage ratios that we desire, and the current ripple and voltage ripple are made as small as possible by selecting the value of L and C. These are the desirable performance characteristics of the converter, which will tell us what should be the operating point. These are the undesirable performance characteristics of the converter. This will give us a boundary on the value of L and C to be used, so that the undesirable performance features are negligible compared to the desirable performance features. The real voltage gain, whenever there is presence of non-idealities of switches, like the transistor switch drop or the freewheeling diode drop, and similarly the non-ideality of the inductor, the parasitic inductor RL by R, which is represented by this quantity alpha. Now, these non-idealities in the switches, conduction drops of the switches, non-idealities in the inductor, which is the parasitic resistance of the inductor, they all affect the ratio, the conversion ratio V naught by Vg. The way we have done the analysis, we write it in such a way that the ideal conversion gain is now modified by a correction factor, which is a function of the non-ideality. For example, when the inductor non-ideality of RL is considered, the parameter which quantifies this non-ideality is RL by R, the ratio of parasitic resistance of the inductor represented as in relation to the load resistance is alpha, and operating duty ratio D and alpha decide how much this correction factor is. So, from the ideal gain, we have now a modifier or a correction factor, which is a function of the non-ideality in the converter. And similarly, whenever the switch has a conduction drop, we do the analysis based on volt second balance, and we represent the results as the ideal gain in multiplication with a correction factor, and this correction factor will be close to 1 if the converter is a good converter, that the parasitic elements or the conduction drops do not affect the performance so much, so that the correction factor on account of the inductor or the correction factor on account of the switch drops will be negligible, or will be the correction factors will be close to 1. For that to happen, the switch drop Vt has to be very much small compared to Vg, and the diode drop has to be very much small compared to V naught. And similarly, on this side, this alpha has to be very much less compared to 1. RL has to be very small in comparison with R. So, these are the parasitic effects and their effect on the ideal performance figures. The real current gain is not affected by any of these parasitic effects. This is an interesting result, because we know that all the parasitic effects that we have been considering, conduction drop of the switch, conduction drop of the diode, then the series resistance drop of the inductor and so on, they are all series non-idealities. They drop a voltage when certain current is flowing, and because they are series non-idealities, they have no effect on the current ratios in the converter, ratios of input current to inductor current, input current to output current to inductor current and so on. And we had seen in the analysis that it is simply the averaging of these currents do not or not affected, averaging of the current is not affected by the series non-idealities, and so the real current gain and the ideal current gain, these two are perfectly the same, minus d by 1 minus d. And on account of these non-idealities, series non-idealities, we have seen that the efficiency of the power converter has been affected, and this efficiency, because of the inductor, is on account of the loss in the inductor, I square R loss in the parasitic resistance of the inductor, and similarly the conduction loss in the active switch and the conduction loss in the freewheeling diode. All these quantities give rise to losses in the converter, and it also reflects on the efficiency of the converter. So, the efficiency on account of the parasitic resistance is this quantity, efficiency on account of the switch is this quantity, and overall efficiency will be the product of this correction factor 1 multiplied by the correction factor 2. So, we can say that there is a loss in gain, loss in voltage gain on account of the parasitic loss in the inductor, and similarly there is a loss in voltage gain on account of the conduction drop in the switch, and overall the efficiency is affected by two factors. One is the I square R loss in the inductor, which is the factor given by 1 minus d whole square divided by 1 minus d whole square plus alpha, and the other one is the loss in the switches, conduction loss in the active switch, controlled switch as well as the uncontrolled switch, and this has efficiency of charging and efficiency of discharging. So, effectively the overall efficiency is the product of these two correction factors, and we had seen that in all these in the boost converter as well as the flyback converter, when the duty ratio goes beyond this number 1 minus root alpha, the converter operates with an efficiency which is less than 0.5, which is not a very good operating point. Losses are higher than what is being delivered to the load. So, the preferred operating range is in the region where duty ratio is less than 1 minus root alpha. Normally, we would keep it even considerably less than 1 minus root alpha, so that the efficiency is closer to 80% or 90%. Okay. What we had seen in the past 1 hour or so is to look at this buck boost converter or flyback converter as made up of a converter cell connected to a voltage source and connected to a load. Earlier we had seen that this cell can be used in 3 different variations. where the throws are on the input side and the inductor is on the output side, and this we called as the buck converter, where V naught by Vg was D, duty ratio. Then we had also seen that if the Vg is connected to the inductor end and V naught is connected to the throws, then this works as a boost converter. It is called a boost converter, where V naught by Vg is 1 by 1 minus D, duty ratio, in the ideal case. And now what we have seen is that the same cell can be connected in a third way. These are the three different ways in which the cell can be connected, where the source is connected to one side and the load is connected to the other side, and the common point is the pole or the inductor of the switch and T1 and T2. And we had seen that in this case the ratio is minus D by 1 minus D. The output has a polarity which is negative of the input polarity, and the ratio is minus D by 1 minus D in the ideal case. So, these are the three different power converter topologies, basic power converter topologies. This is the buck converter, the second one is the boost converter, what you see here, and the third one is the flyback converter, which is this. These converters are all non-isolated converters, that is, the electrically the input and output have a common potential on one side of the voltage. Vg is with respect to 0 and V naught is also with respect to that same 0, and these converters are all called non-isolated converters. So, just before we go into that, we will look at another slight variant of the same converter cell. This converter cell, what you see on the right hand side, is a dual of the converter cell that we have seen before. The first cell that we had seen is consisting of a single pole double throw switch, where an inductor is connected in series with the pole and the three terminals are brought out. And we had seen that it can be converted, it can be connected to a source and a load in three different ways: the buck converter, the boost converter and the buck boost converter. The dual of this circuit, where the switch is connected as before, a single pole double throw switch, but instead of using an inductor, we use a capacitor. There is only one storage element, which is capacitor, and we have seen that in the case of a single pole double throw switch, the capacitor can be connected across the throws between T1 and T2, because there is a circuit condition that the capacitor voltage can never be short circuited, just as the circuit condition that the inductor current can never be short circuited, and so the inductor was connected to the pole. In the same way, the capacitor has to be connected across the throws. So, whether the switch is connected to PT1 or it is connected to PT2, the capacitor is never short circuited. This also has three terminals, and this is a dual configuration of the one that we have seen, and it is possible to connect this as a buck current converter. If we had seen the previous cell as a converter, a buck voltage converter, where it converts Vg to V naught in the previous configuration. Now, we can have a source of Ig and a load of I naught, and this cell, this converter cell can be connected in several ways between the source and the load, and the way I have shown here is a buck current converter. In such a configuration, this is connected to P, these points are connected together, and this is connected here. So, such a configuration, it is a buck current converter. We will see that it can be also Here also we can apply, similar to volt second balance, we can apply amp second balance on the capacitor, the dual property of what we had seen before. The dual converter cell, what you have seen is during the connection is made like this. So, during the T on, during the time the switch is in T on, the inductor current IC, capacitor current IC is IG coming from here, because the switch is connected to T on, IG coming from here and I naught going out of here. This is the on state current into the capacitor. If you see the off state, when the switch is connected to this end, IG is just short circuited through the switch and I naught only is flowing through the capacitor with a minus sign, because it is coming out of that. This is the capacitor current during the off time. So, if we find out what is the total charge into the capacitor, it will be IG minus I naught into T on minus I naught into T off. So, under steady state, the net charge over one cycle in a capacitor has to be 0. This is similar to volt second in an inductor, because the net volt second applied to an inductor over one cycle represents the flux change, and under steady state flux change from cycle to cycle is 0. In the same way, the charge that is supplied to the capacitor during the on time and the charge that is depleted from the capacitor during the off time, they have to be equal to each other if under steady state the capacitor does not gain any voltage from cycle to cycle. If we simplify this, you will find IG into T on is equal to I naught into Ts or I naught by IG. I naught by IG is T on by Ts, which is D. So, this is a buck current converter. The output current is duty ratio times the input current, and this is the perfect dual of what we had seen before, that from a current source of IG, you can supply power to a current sink of I naught using a single pole double throw switch and a capacitor C. The connection between the throws, poles and the capacitor are shown this way, and what we have seen here in this hexagonal box is our switch cell. The switch cell consists of one single pole double throw switch and one capacitor connected as per the circuit laws. This is a buck current converter, and if you just see a very interesting thing, just like a boost voltage converter, we can have a boost current converter with the same cell connected by flipping the cell, where P was earlier on this side, it is connected to the output, and the throws which were on the output side, they are connected to the input side, and now this connection is done over like this, and then P gets connected here. This will become a boost current converter. Here also it is possible to find out during the on time, P T1 is connected here, I naught is completely shorted. In that time, IG flows through C, you will find that IG into T on is the charge on the capacitor when the switch is connected here, and when the switch is connected in the off state, the current through the capacitor is now what was coming in here IG into T on, now it is IG minus I naught into T off equal to 0, and this can be written as IG into Ts equal to I naught into T off, or I naught is equal to Ig into Ts by T off. This is Ig divided by 1 minus D. This is what we call as the boost current converter. The output current is input current divided by 1 minus D, or the output current will be more than the input current. this is a dual of the boost voltage converter and this is a boost current converter. Okay. And in the same way, the third way of connecting the same cell is with the pole at the common point and T1 and T2 connected to the source and the load, and if the calculations are done on the amp second balance here, you should be able to find out that I naught by Ig must be minus D by 1 minus D, which is the same as the buck boost current converter. So, we have seen that this cell, which is a dual of the inductor plus SPDT cell, also has identical 3 variants of buck current converter, boost current converter and buck boost current converter. So, effectively single switch and single energy storage element can be connected in these many ways, 3 variants in each of them, as a current converter or a voltage converter. And we see that in all these converters, it is possible to find out the voltage gain, current ripple, voltage ripple, real voltage gain, real current gain, efficiency, and then the preferred operating range, all of them through the different steps that we had seen. The ideal voltage gain will be done by volt second balance on the inductor or ampere second balance on the capacitor. So, in the capacitive energy storage element, to find out this gain, current gain or voltage gain, we will use the ampere second balance or volt second balance. In order to get the ideal current gain, we will find out the averaging process. Similarly, here also averaging process. And the current ripple is found out by integrating VL and voltage ripple is found out by integrating IC. Okay, dual properties. Integrating IC dt over one period 0 to t will give us the voltage ripple measure, and similarly integrating VL dt for one cycle 0 to t will give us the current ripple. And the real voltage gain is also obtained by volt second balance, but keeping account of the drops that are taking place on account of the parasitic resistances, parasitic voltage drops and so on. Real current gain is again found out by similar averaging process. And then the efficiency can be easily found out as the correction factor which appears on the voltage gain. The real voltage gain and the ideal voltage gain will differ by a correction factor, and that correction factor will be our efficiency. Okay. The preferred operating range is normally found out where the efficiency is closer to 1. In most converters, the closer to unity efficiency is the preferred operating point, because losses in the converter will be small. Okay. All these converters that we have seen up to now, the current converters or voltage converters, they all have one of the lines common, and they are all called non-isolated converters. Even though practically all the converters can be reduced to an equivalent circuit of such a non-isolated converter for the purpose of simple analysis, in real life we require in many applications the load to be supplied power from a source which do not share a common electrical connection. So, such power converters are called isolated power converters. In such power converters, the source side and the load side are not to be connected electrically. As you see here, see this has a source portion and the load portion are perfectly isolated from each other. Electrically, there is no connection between the source side and the load side, so that the potential on the load and the potential on the source can be arbitrary. They can be floating at different levels, and so this electrical isolation between input and output is very essential in many applications. So, what we will see in the next set of lectures will be several power converter topologies which help us to achieve the electrical isolation. Performance wise, they are identical to the non-isolated versions. They also operate with pulse width modulation with a constant switching period and a certain on time and certain off time. All those fundamental basic characteristic features are same between the isolated power converters and non-isolated power converters, but the the isolated power converters provide load power which is electrically isolated from the source potentials, and that is very essential in many applications from the point of view of safety of personnel as well as safety of equipment. So, what we will see will be several power conversion topologies which are suitable for isolated power supply to the load from a source with total electrical isolation. These circuit topologies invariably will use electromagnetic isolation. What you see here is an electromagnetic element with a primary inductance or a primary winding and a secondary winding. The magnetic element can be charged by drawing a current in the primary, and the magnetic element can be discharged by discharging the current into the load in such a way that the power first gets converted to electromagnetic, electrical power is converted to magnetic energy is reconverted to electrical and supplied to the load. So, that way we keep a total electrical isolation between the input and output. So, in the coming lectures, we will see several circuit topologies which provide electrical isolation with a different number of switches, energy storage elements, transformers and so on. And after that is over, we will be able to see a few more operating modes on these converters. The next lecture will be on isolated power converter topologies. So, we will see forward converter, flyback converter again and bridge converters and several of them. So, thank you very much.